All right, thank you everybody for being here. This is the 70th annual Senior Design Conference at Western Michigan University. This is a capstone project that allows students to show their technical skills, creativity, communication skills, team building skills, and innovative ideas. If I'm not mistaken, they began this project months ago. It also shows their dedication and commitment and the ability to meet goals despite foreseen and a lot of unforeseen circumstances. Before we begin, I'd like to give a special welcome to a few parents, Margaret Herman, Kevin Herman, Steve St. Clair, and Mindy St. Clair. So without further ado, we'll begin.
Right. Hello, good morning, everybody. Thank you for showing up today. We really appreciate the turnout. We are the Tricycle Retrofit for Fluid Power, and we will be representing Western Michigan University in the National Fluid Power Association's Fluid Power Vehicle Challenge. So our project overview. So we pretty much wanted to create a competitive vehicle that we will be using to take to a competition actually later this week in Iowa. We have specific design constraints that were given to us by the NFPA, so we had to really make our design based off of a lot of those constraints that were given to us. And the hydraulic components that we have on this were also provided to us by our sponsors with the NFPA. I'm going to turn this over to John.
Thank you. So this is our project scope. We had this in the beginning. This is what we plan on doing. So our plan in the beginning was to design a fluid power vehicle set up on an existing bike. So we bought the bike, stripped it down, and then added the hydraulic components. And then we wanted to build and test that throughout the semester, ensuring that it was maximized efficiency. And then finally, we wanted to compete in this fluid power vehicle challenge. The project objectives from the start was to maintain safety with moving chains, the fluid, between environmental and personal safety. It can get pretty bad if those right things aren't put in place. We also wanted to complete a working assembly of the vehicle, which sounds simple, but to be honest, it's actually took us up to like about this last week to get that finished. Our design constraints put forth by the NFPA, we wanted to make sure, they wanted to make sure this is a human-powered vehicle that ended up having hydraulic power to actually run the bike. They also wanted to ensure that it wasn't over 210 pounds. Right now, we are close to 100, a little bit over 100, so we are far below that. And then also a constraint that was kind of put on us, not intentionally, but we wanted to resolving complex part availability. From the start, those parts were with supply chain issues. It's hard to get a lot of those, so we had to resolve those conflicts throughout the year. Project requirements. This is a very basic setup of the requirements for this project. First one, the rider is going to pedal the bike, and instead of like a typical bike where the rider pedals and the back chain runs the bike, that back chain is actually connected to the pump rotary. And when that pump rotary spins, it will pressurize the fluid into the motor. And the motor is the exact opposite of the pump, where the fluid goes through it and the rotary, the motor spins. And then from there, the motor rotary will spin as it is connected to the back axle of the bike, and then that propels the bike forward. Performance criteria are one that we want to make sure we did from the beginning, like I said, was safety. That was always on the top of our list. We wanted to ensure that it was safe for the rider and, of course, the environment. Secondly, we wanted to maximize performance for this competition this week, actually. And a lot of that involved like component selection, hose size, hose angles, length of hydraulic fluid travel, a lot of stuff, a lot of calculations in there for that. We also want to minimize vehicle weight, which kind of goes with maximizing performance. Obviously, minimize weight is easier for the bike to run. So this is our design process. So this is a simple design process that they will go in more detail later. We started by understanding this project, a lot of research of last year's components or bikes, understanding how hydraulic components work, as we didn't really have any experience in it, and then go on into this project. We also wanted, and then the next step was to research this project, and that involved understanding how the hydraulic components worked together, and how the hoses work together, and how the fluid worked with all those components. And also within the next step was to develop the project. And this involved a lot of calculations for finalizing our component selection, so understanding how the fluid went through the system. And then the next step was to plan, and this involved precise CAD models that we planned to exactly place the components, making sure that the prototyping and testing phase was as smooth as possible. The next step was prototyping. This involved a lot of manufacturing components and ensuring that all the actual hydraulic components had a place to sit and not move around. And then our final phases was test and improve. And I can safely say that we probably had 40, 50 iterations of this testing and improving phase. A lot of this last month. It's been long hours trying to make sure that this bike was working as efficiently as possible. So now I'm going to hand it off to my teammate, Hannah.
All right, all right. So the first big decision that we had to make once we decided that we were going to do a tricycle for our bike selection was to actually go through and see what sorts of options that we had. So we ended up picking a trike mostly because it gave us 3 points of contact. Ground is the safest, and it allowed us to have the most amount of like customization available on the back. So we kind of had a multi-platform. So we had 2 different Schwinn options as well as an SLSY. Our 2 Schwinn options actually ended up being aluminum frame. So we weren't sure at the beginning of this project what sort of modifications we might actually need to make to this. And due to aluminum not being very good to weld, we weren't quite exactly sure that the aluminum frames is what we might want, even though it typically weighs a little less. Also with durability, that was kind of another reason that we ended up not wanting to have aluminum frame. The other thing was our load capacity. So looking at our 3 options, the SLSY actually gave us the most amount of load capacity from the manufacturer's website. And option 3 actually also is made of steel. So this allowed us to, we wanted to make any sort of modifications of welding, grinding, or anything like that. We have the tools here in the shop to actually be able to make those modifications that we wanted. Over to Jake now.
Yeah. So I'm going to go over some of the hydraulic components that we have in our vehicle. Some of the basic components that are used in many different hydraulic circuits. So we have the pump, which is used by the rider. When you're pedaling the vehicle, it will provide pressure to the system. The hand pump, which any team member throughout any of the races will be carrying, we have 10 minutes to pressurize the system. So use that to try to get your PSI up to 3,000 in the accumulator. Our motor, which takes that pressure and releases it to the rear axle to give you your movement. The reservoir, which is this tank here, that is kind of all of your fluid throughout your system is routed from there. So if you need fluid, it's kind of like your gas tank in your car. Your accumulator, which is right here, that can hold up to 3,000 PSI and can provide you your start. It's very hard to get these vehicles moving at first, so it's very nice to have something like that on there. We also have the manifold, which I will talk about in a second.
So this was our final CAD rendering, and this kind of shows like our best component, or our most important components that we have. So the reservoir with the red arrow, that's going to be what we wanted to be at the highest point because that is what's going to be feeding our entire system. So we wanted to make sure that kind of gravity was helping us out as much as possible to make it more efficient, as well as the accumulator. We also wanted that to be going up and down, so then that way we would get the most amount of pressure coming out of that thing. Another thing, we have our hand pump here. That's how we're going to manually put pressure into our accumulator. That was something that when we originally started, we had to actually beef up the platform right there because when we were going, putting pressure into the system, we were bending the platform a little bit because we ended up choosing aluminum for that platform. So we did run into that problem. However, we found a solution for that. And then the other thing is that these custom brackets that we'll talk about a little bit later, those hold our pump motor as well as our internal gear hubs. And so here on the left is our original pump and motor setup. So we originally had our internal gear hub right behind the rider's seat. However, after looking at our system and determining to make it a little bit more efficient, we decided to move it over to the other side. It also allowed us to have our chain meet up better with the internal gear hub to make that more efficient as well. And then we ended up rotating the pump due to rotation. That's it.
So our manufacturing process started out with constructing our bike together. So it came in a box. Once we put it together, we took some measurements. We got ready to make the brackets, platform, and some different prototypes. The prototypes we made with 3D printer allowed us to put an adapter on the hubs that would allow us to put sprockets on there. We also made a temporary holding for the battery and for the manifold. So after we got done with those, we started our assembly process. This is where a lot of our time took place. When we were starting on building, there was a lot of components that might not line up exactly where we wanted them to have a smooth drivetrain. So we had to edit those quite a few times to make sure everything was running smoothly. We had to connect all of our hoses. We used thread tape to make sure that nothing's going to leak out of our system. There's actually pressure in there right now, but you would never know because everything's airtight. We also had to troubleshoot our system a lot. That included riding the bike, trying to get everything working efficiently, and making sure everything was connected as we designed. The hydraulic circuit that we originally constructed is right here. So this is a very basic circuit, and we had solenoid valves that we would be able to connect to electronically. And after that, we got a manifold for our system. This is kind of like the heart of our system. All the different passageways go through it, and it directs all of our lines. It makes our system much more efficient and easier to use, along with this electrical control panel we have up here that we can adjust our system at any given time. This is the new circuit that we made after getting the manifold. And with this system, we have 4 different modes. These 4 modes are the pedaling mode, which allows you to pedal the system and create pressure in the system, releasing it to the rear axle and giving you movement. This is our primary circuit, so we want, even if the battery dies, we want this circuit to still be working. So if the system shut down, it will still go back to this and we can still pedal on the races. Our next is the charging. So this is important because we have 10 minutes before each race to charge our system. The next one is the boost. This one is my favorite. We click a button on here. It starts the vehicle right away. That's going to give us our launch for the start. The 4th mode is regen. So at one point in the race, we have to stop and switch riders. So with this, we're able to charge our system up a little bit more. That way we have another kickstart at the beginning. Pass this up to Dan.
So, for our testing process, we kind of tried to break all these systems down individually, especially the hydraulic circuits themselves. With those different drive modes, we wanted to test them in an isolated condition to make sure that we understood how they worked and understood how the bike would operate in all 4 of those conditions. So testing process actually took a lot of time, just assembling each circuit individually to make sure that it performed as expected. Once we had a good idea of how they would perform, we connected everything to the manifold, which is, like Jake said, a very simple and easy way to control everything from one location. Manifold has been a great addition to our project, and we've done some testing with that over the past week or so, and it has also performed as expected. Kind of breaking things down for you a little bit more here, we'll talk about the physical layout of everything. So when you start to pedal, there is a very large sprocket on the pedal axle that you see in front there. And what that does is that gives us a very good mechanical advantage to get the first internal gear hub started. And so the motion that you provide with your pedals is actually going to spin that axle, or that axis, sorry, that the gear hub is on. That has planetary gears inside that are shiftable. There's 3 speeds. And so that will scale up your RPMs from the input to the output. And that output is connected by another chain to our pump. So the goal here is to generate as much motion in that pump, as many RPMs as possible, to generate as much fluid flow as possible at the start of things. And then the opposite happens on the backside. You want to scale that RPM back down to a usable speed to get you started and maintain that speed. But you need to have enough fluid flow and enough fluid pressure to actually move the bike itself. So you need to generate high torque with low speed. So we've achieved this by having an internal gear hub on both sides. That's really nice. We can shift either our input or our output to make it easiest to ride under all conditions. These internal gear hubs are actually something that are typically found on the inside of your rear wheels on a bike. It's a self-contained sort of transmission that it's not exposed to any elements. Typically on a simple bike, you've got your derailleur that scales the chain up and down on different size gears. This is all internally assembled, and there's really no maintenance required with any of that, and it's very, very low risk. It makes it easy to set up a chain on each side for us and shift without having to worry about too much alignment. So we've done some calculations here with some expected outputs. This thing is very difficult to pedal. So once you get started with the help of that accumulator, the main goal is to maintain a constant riding speed that is low effort and has a high system output. So these hubs really help, and on our races that I'll get into a little bit later, we'll be going up and downhill. So we're excited to be able to shift this thing and kind of basically handle whatever the competition throws at us. Again, talking about some of that mechanical advantage, we have different sprockets on these hubs that we can actually swap in and out. So we are allowed to modify the bike between races, and there's the stock cassette on the rear axle, which is kind of like your standard setup where the chain moves up and down. So for these different races that I'll get into later, it's on the next couple slides, we can make our system either have a higher top speed, or more torque output, or a higher efficiency so that it's easier to pedal. So that accumulator is really going to come in handy with this efficiency race that we've got coming up. That's probably the most difficult part of riding this bike, is getting started. So we charge pressure up either through pedaling or through pumping a hand pump, store that pressure for later, and then release it into the system. We can actually switch that off like Jake demonstrated and then take over pedaling, and it's a pretty nice system. Really like that. So these competitions will be held in Ames, Iowa. This is one of our sponsors, Danfoss. This is their test facility here. We'll actually be traveling there tomorrow to test the output of our system. And we've got a pretty good idea of how it'll work. We've done some time trials, and that'll be what we're up to for the rest of the day. Just making sure that we're ready to give this our best shot. These races that we've got coming up, there's 3 different tests. The first is a sprint, and that's mainly just top speed, point A to point B, how fast can you get there? It's based on time. There's a accumulator test, basically in the efficiency race. There's no pedaling allowed for that one. You just click the button, you go as far as possible. That tests the output of your system to make sure that you've designed something that's efficient. And then the endurance race is 20 minutes long, multiple laps. Not only are you scored on whether or not you finish, and if you finish before those 20 minutes, but also just most laps completed if the rest of the schools don't do well. We're competing against 10 other universities throughout the nation here. There's actually 2 different competitions that are split up, and I believe 30 schools in total this year. So we'll be competing against about 11 or 12 of those in Iowa. So in conclusion, we've done quite a bit of work with our system here. We started with a very basic bike frame that was already predefined, and we used that as sort of a blank template to set up a new drivetrain on. Getting the bike was very exciting. We received that back in November. We did some measurements, some testing, CAD models and things to kind of wrap our head around this at first. Once we did that, we started assembling our drivetrain and our hydraulic circuit, and of course we ran into issues with parts availability, and we ended up having a lot of challenges that we had to solve for ourselves. So I believe we've come a long way. We're very excited to compete in the next couple days here. There's a presentation we'll have to give on our setup there, and we're excited to talk about all the challenges and resolutions that we've made for ourselves. So we'd like to extend some thank yous before we conclude here. Dr. Rodriguez and Dr. Chowdhury have been infinitely helpful with our project. They've given us endless input and endless hours in the lab as we've been working, as well as some manufacturing people here at Western, Mike Conkle and Andrew Wyman, have helped us actually put this thing together, which has been a huge help. Samson Nicky has spent also many, many hours in the lab with us. Our industry technical advisor is Jay, and the NFPA program manager is Stephanie. Those are the 2 that have been in touch with us the most from basically day one to kind of guide us through the NFPA process and how they want us to assemble this bike. Had some good exchanges with them, and they've been infinitely helpful as well. So I'd like to open up time now for any questions or any comments you have about our bike. I'd like to hear from you. Thank you.
This is the first time that this cycle competition take place, or is it the same as previous years? And if it is the same as previous years, have you delivery tested to see where you fall within past performance?
Right. So, the Fluid Power Vehicle Challenge was actually previously called the Chainless Challenge, and this has been around for about 10 or 15 years now. Western has competed in this in previous years. The past 2 or 3 years haven't really been all that much thanks to COVID, but we've got some expected results for our bike. We compared those to previous years, and we're fairly optimistic. Thank you.
Thank you.
Is there a portion of the competition that you think your bike will do exceptionally well in?
So honestly, we've tried to design for all three of them because with the scoring system, you kind of need to compete in all three to be competitive. Overall, we're very optimistic about the efficiency test. I'll probably read right for that, and I'm fairly light guy. So with the tests that we've done so far, we can travel probably a couple hundred feet on just the accumulator power alone. Later today, we'll be kind of swapping out some of those sprockets to see if we can get that any higher. But as of right now, that's fairly competitive. Endurance for sure. I know Jake is a biker in his spare time, and he's got some good legs on him, so he'll get us moving through that one for sure. So overall, pretty optimistic, but I'd say endurance and efficiency are probably our best bets. Thank you.
Any other questions in the room?
The thing in the back. Sorry, what was that?
So there's actually not a mechanical advantage of using the hydraulic system. The competition is more of a challenge in itself to get the bike to work. It's actually much more efficient to use a normal bicycle. They're very efficient, and adding all these components on it and the extra weight and converting the power, you have a lot of loss. But it's just part of the competition to see if you can make the system work together and see how well you can make it.
Thank you.
Were there any questions online? I don't see any.
All right, congratulations. That was a great presentation.